Welcome to the Tech Circuit. This video, intended for field technicians, is about the fundamental and commonly encountered series circuit. And we'll cover why series circuits are relevant, series circuit fundamentals and theory, a series circuit example, and a real-life example of an electric range failure based on the concept of the series circuit voltage divider. What are series circuits and why are they relevant? The series circuit, which is a fundamental electrical configuration, is commonly encountered by technicians. They appear in electric dryer auto modes, gas dryer and gas range ignition systems, and most commonly by virtue of failure in high current circuits. Series circuit fundamentals. In a series circuit, you have two or more loads connected end to end like this. You will, of course, have a voltage source. The total resistance of the circuit, in other words, the resistance that the voltage source sees, is the sum of all resistances. The current in the circuit is the same through the entire circuit. So the current here, here, and here are all the same value. The supply voltage is distributed across the loads in a way that the sum of the voltage across each load is equal to that supply voltage, a phenomenon known as the voltage divider. Series circuit example. Let's do an example by assigning some values to this circuit. Suppose you have a voltage source of 240 volts. Let's call this load R1 and give it a value of 10 ohms. This one, R2, also with a value of 10 ohms. The total circuit resistance would simply be R1 plus R2, or 20 ohms. The current will be the voltage source divided by the total circuit resistance. Per Ohm's law, we have 240 volts divided by 20 ohms, or 12 amps of current flowing through the circuit. A voltage divider is now formed by the two loads. This occurs because the 240 volt source voltage is distributed across R1 and R2 in a way that depends on their respective resistances. Now we can easily arrive at those values by again using Ohm's law. The voltage across R1 is simply I times R, or 12 amps, times 10 ohms, or 120 volts. Since R2 has the same resistance, the same applies to it. Notice that the sum of the voltage drops is equal to the source voltage. That's how voltage dividers work. Also notice that each voltage is the same. That is only because the resistance of R1 and R2 are the same. If they were of different values, the voltage drops would also be different, but would still add up to 240 volts, which is the source voltage. Another aspect of series circuits is that the loads distribute the power in a way that is also proportional to their respective resistances, but the total power absorbed by the loads is equal to the total power delivered to the circuit. In our example, the total power delivered to the circuit per the power equation is P equals E times I, where E is voltage and I is current. And that is equal to 240 volts times 12 amps, or 2,880 watts. You might have guessed that each load, since they are of the same resistance, is allocated 1/2 of the total power, or 1,440 watts. And you'd be right. That's because using another power equation, P equals I squared R, you would have 12 amps squared, or 144, times 10 ohms, which is equal to 1,440 watts, which is 1/2 of the total power allocated to the circuit. So how is this all relevant to field technicians? It's quite relevant, actually. Let's do a problem based on something that technicians encounter quite frequently. Suppose you have a 240 volt electric range with a bake element that has a resistance of 20 ohms. The terminal block that the cord is connected to has a loose connection that has a resistance of 4 ohms. The customer complained that the oven was taking a long time to preheat. So the schematic that we just drew depicts this case. Here's your voltage source, your loose terminal block denoted by a resistor of 4 ohms, and your 20 ohm element. What we have here is actually a voltage divider. So some of the supply voltage will appear across the element while the remainder will be lost across the terminal block's loose connection. Let's find out what they are. First, we can easily determine the circuit resistance, which is what we will call R block plus R element, for a total resistance of 24 ohms. This dictates our circuit current. which is simply the supply voltage divided by the resistance, or 240 volts divided by 24 ohms, or 10 amps. With that, we can find out the voltage across each component here. The voltage across the terminal block, or V block, is 10 amps times 4 ohms, or 40 volts. This, by the way, is the voltage that is being lost in the circuit due to that loose connection. The voltage across the element is 10 amps times 20 ohms, or 200 volts. Note that the two voltages add up to the supply voltage, as they should. So this means that the loose terminal block is robbing the circuit of 40 volts. It is also causing the total circuit current to be less than normal due to the extra resistance. Now we can determine the power output in watts of the element and the terminal block. The easiest power equation is P equals E times I, or voltage times current. Thus, the power output of the element is 200 volts times 10 amps, or 2000 watts. Power output of the terminal block's loose connection, or the heat output of that loose connection, is 40 volts times 10 amps, or 400 watts, which actually amounts to a lot of heat output for a terminal block. Thus, the output power of the element is significantly less than normal. How much less? Well, normally the element will have 240 volts across it and 12 amps of current through it. This means it should normally have an output power of 2880 watts, or 880 watts more than with the loose connection. This means that with the loose connection, it is outputting 2000 divided by 2880, or 69% of the normal power. Hence the long preheat time that the customer complained about. So there's a real-life case that can be explained and even quantified by the voltage divider concept. I hope this video on series circuits has been interesting and informative. If so, please give it a thumbs up and subscribe to this channel. See you in the next video.